Welcome back to Nick Does Maths. I'm your host Nick, and here is some maths, and we are going to do it, and that will be great fun. This is an odd little question that was posted over on the Lun Gang subreddit. Go check it out. Great source of some interesting and quirky little maths questions. Really there to challenge what we know of mechanics. Now, there is a lot of blurb. This is like a 20 plus mark question. So, we're going to flash it up on the screen now. All right, pause if you need to, go back and check it. There's 4 different parts of it. I've sort of paraphrased it over here. Let's see what we can do. All right, you can always go back to the beginning of the video, go read the exact wording of the question, but I've got the majority of it here. So what do we got? We've got 2 spheres that they are stuck to the floor. They can't move from the floor, all right? Small one radius little r, big one radius big R. They are a distance r plus r away, small plus big R. On them is laid a non-uniform plank, non-uniform, that is very, very important. These are both rough, so there is friction at A, there is friction at B, with coefficient mu A and coefficient mu B. All right, and the whole thing is in equilibrium. Now, going through this question, I've made a couple of assumptions, because otherwise it doesn't work. So we're going to assume it is in limiting equilibrium. All right, which is its, so friction is operating at its maximum level. Okay, if mu A was any worse, then the whole thing would collapse. Okay, and also, if you go back and read the question, part B is asking you about the magnitude of the reaction. I've made the assumption that it means the total of the 2 reactions at A and at B, and you'll see why. I mean, if you can find an error in my working, do let me know. Because I've tried this a few times and I can't figure it out otherwise. So, okay, let's put in some forces. First things first, we have the weight of the rod, of the plank. That is capital mg. We are going to put in some reaction forces. Reaction force at A. Reaction force at B. We also have a friction at A and a friction at B. Why am I putting the frictions going along the plank like this? Well, if you were to put this something on these 2 circles, the way gravity is going to want to pull it down is down that way. Therefore, the friction is stopping it from going. Stopping it from doing that. Little bit of geometry that might be helpful for us in a little bit. ... The classic one from mechanics. We're going to whack a little theta in there. Interestingly, though, so I've redrawn this diagram a little bit better, but we'll see how that goes. All right. This is my best live drawing. Part A, we want to find the expression for theta, tan theta, in terms of capital R and little r. Now, the way we're going to do that, the thing we need to notice here, let's take my green pen, is as follows, is you need to change a little bit how you view this thing. All right, you need to change a little bit how you view this thing. Now, take this whole thing and look at this axis of symmetry down through the 2 centers. What you will find is, in fact, that angle there is theta over 2. The whole thing is symmetric. The whole thing is symmetrical because you will have completely similar triangles, and we can also use that to view that distance is also r plus capital R. So you've got some nice symmetry along that symmetry along that axis. That's going to help us. Now, what this also means is that, in fact, if I was to just draw this horizontal line along here and go up here, now let's take that little circle out and see what we can do with it for part circle, that little triangle out, and see what we can do with it. Okay. Now the angle is theta over 2. Okay? The angle is theta over 2, corresponding angle to that theta over 2 there. Okay? The distance at the bottom is capital R plus little r. That's supposed to be a nice square root. Now, this distance up here, I hope you can see, is capital R minus lowercase r. Let's stop clutching that for dear life. And now we're up and running. Because what we can say is that tan of theta over 2 for this geometry to work is capital R minus little r over r plus r. Now we want an expression for tan theta, but because we is well smart, we know that tan theta is tan of 2 theta over 2, which is 2 tan theta over 2 over 1 minus tan squared theta over 2. Okay. So what does that do for me? So we end up with 2 times r minus r over r plus r over 1 minus r squared over r plus r squared. Now I'm going to multiply, you can think of this in a myriad of ways, but I'm going to multiply the numerator by r plus r squared, and I'm going to multiply the denominator by r plus r squared, which gives me 2 r minus r plus r over r plus r squared minus r minus r squared. Very little bit of jiggery pokery. So this is tan theta, remember. That will give me 2 lots of r squared minus r squared. I hope you can listen, you can hear the capitals, the uppercase, lowercase in my voice. A bunch of cancellations will happen here. That is 4 capital R little r. So we end up with this result. Tan theta is 2, is not that. It is r squared minus r squared over 2 capital R little r. Okay. And in fact, what I'm probably going to do here is just keep as much board as possible, because this next bit is a little bit fiddly. So we're going to whack that back up here. But hopefully you can see the geometry of what's going on here. The key really is seeing that line that goes down through the 2 centers. So just think of it of aligning the 2 centers. Just shift your view along that line. Basic bits of circle theorems will tell us that that length is equal to that length. And of course, this bisects the big angle. So that angle is equal to that one. So if that is tan theta, that is theta, this little angle here is theta over 2. Okay. Whoop. I mean, whoop. Whoop. We'll keep our answer up here at the top for future reference. Tan theta, what was it? R squared minus R squared over 2 capital R little r. Yes, my little crib sheet over there. Okay, now we actually have to do a bit of mechanics. So first thing we're going to do is we are going to look at the forces up and down the rod. So really my I and J directions I'm going to be taking here are going to be in the direction of the plank or the rod, I can't remember what it's called, and perpendicular to it. So what have I got going up? I've got the friction at A, I've got the friction at B. What's going down? I've got mg sine theta. Okie dokie. What's going perpendicular to it? I've got RA plus RB, and that's got to equal to mg cos theta. Now we can also take moments about A, and I might as well just do that now. So what is pulling me clockwise about A? Mg cos theta, and that is a distance of r plus r away. What's pulling me round the other way? R plus capital R, and it's not a distance of r plus capital R away. That is the whole point of this. That is the whole point, you ridiculous child. Times x, but that is there. So equation 1, equation 2, equation 3. Now that is true no matter what. These are going to be my basic equations of motion, and in fact, like I said, the question doesn't explicitly point this out, but we've got to assume we are in limiting equilibrium, because otherwise we can't use the mu's. So that is mu A RA, and that is mu B RB. So far, so good. So what do we want? So part B is saying, what if we're in a situation where, first of all, we're going to make the two coefficient of frictions identical, and the two reaction forces are identical. What can we say about the reaction? Now they say that the modulus of the reaction force is this. Just follow my working. If you can spot the error, please do tell me. I would be thoroughly grateful. So what ends up happening? Well, equation 1 in this case ends up becoming 2 mu, and let's just call it reaction at B. I'm not going to use capital R because I've used capital R for the radius there. So 2 mu RB, that's fine, because these become the same thing, is mg sine theta. The second equation becomes 2 RB is equal to mg cos theta. And we can do a couple of things. We can first of all just divide them. 1 over 2 will tell me that mu is equal to tan theta, so that's quite handy. And then what I'm going to do is the classic square and add them. So I'm going to square and add them. So I get 4 mu squared plus 4 lots of the reaction at B squared is equal to mg squared, and then that is times sine squared theta plus cos squared theta. And that's the whole reason for doing this, is because then they disappear. Now, 4 times, so what we actually want, mu is tan theta. So that's tan squared theta plus 1, RB squared is equal to mg squared. And this is where this is going to come in. And in fact, I'm going to do this up here. I will put my result up here. So let's do a bit of working down here. Let's do it in blue. So we need to have a little look-see at what tan squared plus 1 is. So tan squared plus 1. Now, the plus 1, I'm going to preemptively write it this way. All right, that's my plus 1. If you expand and sort out the top here, so you will end up with an r to the 4 minus 2 r squared little r squared plus r to the 4 plus 4 r squared little r squared over 4 capital R squared little r squared. And the top very nicely simplifies to r squared minus r squared squared. Okay? I know, there's a lot of squares and r's and whatever, just like bear with me. So what this tells me is that 1 plus tan squared theta, which is also sec squared theta, by the way, which might come in handy later, is r squared minus r squared squared over 4r squared r squared. In my mind, I know exactly when it's a capital R and when it's a lowercase r. You've just got to go with it in context and reading and seeing at the same time. So, using that, I can now square root everything to get 2 times square root of this mg. And this does give me sort of what they were getting at, which is r, capital R, mg over r squared minus r squared. That is a terrible r. Okay? And then because there are 2 of them, there's an RA and an RB. The total reaction force is twice that, which I think is, oh. Copied that out wrong. That's a plus. That's a plus. That's a plus. I might have said that wrong when I did my tan squared. Go back and check it. If you were thinking that should have been a plus in there, it absolutely should have been. It absolutely should have been. Yeah, because you go from the minus to the plus, and that's the neat little trick. Okay. Right, what does x need to be? What does x need to be for this to work? So we've now got to go back to this guy here. We've now got to go back to this guy here. Let's try and see what we can do over in this corner here. So we're going to go back to equation number 3, which was this one here. Now this is where stuff is quite cool, because cos theta, I'm going to write that as mg over sec theta times x is equal to r plus r times rb, which is r. Am I going to run out of space over here? Capital R mg all over r squared plus r squared. Am I on the right direction? I think so. Now, the mg's cancel out. Badonk, badonk. So x becomes r plus capital R, r times capital R, times sec theta over r squared plus r squared. But what is sec theta? Well, it is square root of that. All right? And sec theta is r plus capital R, r, big R, and sec theta is r squared plus little r squared over 2r capital R. And I missed out here, capital R squared, the lowercase r squared, and a whole shebang of stuff cancels out. You go away, and you go away, and you go away, and you go away. So I make it, in fact, that the centre of mass needs to be halfway, well, needs to be the average of the two radii. So that's cool. Did we make any whoopsies in there? Mg cos theta x, that's mg over sec theta, is r plus capital RB times the reaction at B. My reaction at B is solid, RRmg over that. I mean, that feels like a good answer, doesn't it? That feels like a solid little answer right there. I quite like it. Feels good. Let me know. Do let me know in the comments, and I can always post a big apology video if that went a bit wonky. All right, that is part B done. That is part B done. All right, and actually I'm just going to put my answer here for x. Don't know why, but it feels nice. There we go. We've got our values of tan up here. So let's go again. Let's go again. Now what does the question want us to do? It is saying, right, ignore all of that. Let's just go to our more general sense. Can you find x? All right? So in our very general sense, where is the centre of mass, right? This is our situation. This is what's going on. It's in limiting equilibrium. Everyone is happy. Therefore, can you use that to find where the centre of mass needs to be? I can. Spoiler alert. Like, for realsies. Having said that, I need to now remember how. Yes, so I am going to start, because, right, so the equation I have that has x in it has an RB. So the first thing I'm going to do is use these two to cancel out RA. So I'm going to do equation 1, take away mu A times equation 2. All right? Now, you will also quickly see why this is going on, but I can see there's a mu B minus mu A in there. All right, so that does feel like something that could happen. So mu A RA minus, I'm going to times all of this by mu A. Times all of this by mu A. You get a mu A, and you get a mu A, and you get a mu A. Mu A, RA, they cancel out. I'm subtracting. So what am I left with? I'm left with a mu B minus mu A lots of RB equal to. Let's factorize out the mg. I'm left with a sine theta minus mu A cos theta. And actually, now this is where we're on the lookout for things that we recognize, right? Look here, I've got r squared minus r squared over 2rr. That's tan theta. That there is tan theta. So I've got something tan theta minus mu A. Well, actually, we're not far off. We're not far off at all. But let's take that now and plug it back into equation 3. mg cos theta x is equal to r plus r times rb, which is mg sine theta minus mu a cos theta over mu b minus mu a. There's a lot of stuff going on here that is filling me with confidence and joy. Now what am I going to do? Well, I want to divide. Well, first of all, the mg's go bye-byes, as we might expect, fairly independent of the mass of the Planck. Let's get rid of this cos theta. So let's divide everything here by cos theta, and let's divide by cos theta. And we end up with x is r plus r over mu b minus mu a. And what are we left with? We're left with our tan theta minus mu a. And we don't need to rewrite, well, I'm not going to rewrite it here, but tan theta is r squared, is this thing up here. Do you know what? Every time I say I'm not going to do it, I end up doing it. So let's just do it. It's r squared minus r squared over 2rr. Hey, presto, Jiminy Cricket. I might even add a bish, a bash, and a cheeky bosh. That is the result that we want. Woo! Cool. Kill. That's what I mean, right? My assumption here that these, like, all the other working leads to this. So, I don't know, it feels like maybe my assumption was right. Please, if you can find out where that 2 comes from, please do tell me. Okay, now, what are we going to do? What we're going to do is we are going to, if we go back to the original question, maybe flash it up again quickly. What we're going to do is we're going to hang another mass over here to the left of A, of weight W, Okay? And the question is, what is the largest weight I can hang here? And I say here, because it is going to be another R plus capital R to the left. What is the largest weight I can hang there? Before the whole thing collapses, all right? So I need a W in here such that I'm in limiting equilibrium. So everything is at its absolute limit. And here is the key thing to understand about this, is when you are doing that, what does that mean? It means I've hung something so heavy on here that the whole thing is just about to topple or slide, right? It's all about to just come collapsing down. That is the idea. Now, what is our absolute limit of what's going to go on here? Well, at the very point of me putting too much weight, what will happen is the Planck will be just about to pivot about A, so it'll be just lifting off from the sphere up here, or the circle, whatever you want, which means it will no longer be in contact. So what happens for this part, which I'm going to, again, give myself a little bit of room here to work with, I'm going to have to change these equations anyway. Do you know what? I'm just going to redo all the equations for part C. Because we're going to have to rethink about what's happening. Because what it is this no longer exists. As far as the rod is concerned, that sphere is no longer there because this is just lifting off from it. It is just lifting off from it. So what do we have now? All right, it's just lifting off from there. Well, these are the forces we still have. These are the forces that we still have. And we do the same thing. So let's look at what's happening perpendicular. It's not as bad as you might think. we've got the W plus mg cos theta has to equal to the reaction force. They both, the geometry there is identical. I've just pre-factorized that out. And then going up the slope, I've got W plus mg sine theta is equal to the friction at A. And then we can look at turning effects. What have we got? I've got the mg cos theta times x is equal to W cos theta times R plus R. I'm not entirely sure which ones I'm going to use yet. Not sure yet, but let's just see what we got. So we want to find the maximum weight. So we want to find W. What we are trying to solve for is W. What's quite nice here is that the cos thetas go away. All right. Okay. So I think, by and large, we can just use this. All right? We can just use this. Because what we actually get, if we just use this equation here, right? The friction and the reaction force will sort themselves out, is the idea here. The reaction and the friction force will sort themselves out. But what we are going to do is we are going to say, well, W is mgx over R plus R. Now we do need to put in this value for x, which is amazing. But all it does is you have a look, is these two terms will cancel out. So essentially I end up with an mg over mu A minus mu B over R squared minus R squared over 2RR minus mu A. And that's my attempt. That's my attempt at that one. That is the best one we can. The key to remember here is x is where the center of mass is, and we determined that earlier, so that cannot change. That has not changed. That is still what it is. That is still the same rod. It's still the same situation. Okay? We figured out what it was by saying, well, our mu A and mu B's are such that it's in limiting equilibrium. I had to make that assumption for any of this question to work, is my belief. Please let me know if I've missed something. This is very much I've done my best here, guys. If you've got anything better, just reach out. I'd love to start a conversation about it. This was a brilliant question to give a go. No actual further maths content in it, but it's very much like a step question in what it's asking you to do in terms of logical reasoning, which is phenomenal. Okay? All right. I think that's enough for today. Pretty long one, that one. Check in next time. Make sure you subscribe, like, and hit the bell so that you don't miss the next video. See you soon.